Okay, so let us now discuss Stokes' theorem. This Stokes' theorem is a generalized version of Green's theorem that we already covered, right? So what is this theorem says? So let me write down the statement first. So this theorem says that if vector f is any continuously differentiable, so we have vector f to be continuously differentiable vector point function and S is any surface bounded by the curve C, then the integration over the closed surface C, over the closed curve C of this vector f dot with dr, that means the tangential direction of this vector, is equivalent to the surface integral which is taken over curl of vector f dot with n cap ds. Now you can clearly see that this definition is very similar to that of Green's theorem, but the difference here is that this is a generalized version. In Green's theorem we had this dot with k cap vector, right? Here we have the vector n as the unit normal vector at any point S, which is drawn so I can write which is drawn according to the right hand screw rule, right? So this is the statement for this Stokes theorem. So let's see a question which give you an insight about this theorem. So the statement for the question says you are to verify Stokes theorem for the vector f. So vector f is given to be x square minus y square I cap plus 2xyj cap in the rectangular region in xy plane bounded by the lines x is equal to 0, x is equal to a, y is equal to 0 and y is equal to b. So let us first visualize our given region. So here if I draw this coordinate axis, so this is your x-axis, say this is y-axis, this is z-axis, this is origin. So the line y is equal to 0, this one give you the x-axis only, right? And the line y is equal to b, suppose this point is b, so this is this line. So this is your y is equal to b, this is y is equal to 0, x is equal to 0 is your y-axis only, right, this one. And your line x is equal to a, suppose this point is a, so the line this one, so this is your x is equal to a line. So your region of interest here is this particular region. So this is the region, and here the curve is defined in this anti-clockwise direction, so that its direction is taken as positive, right? So this is what we have. This is a region and the vector f is given by x square minus y square I cap plus 2xyj cap. Now we are to verify, so according to Stokes theorem we are to verify whether the surface integral over S of curl f dot with n vector ds, whether this quantity, this is equal to the quantity integration over closed curve C of the vector f dot dr. So we are to verify this thing. So let's call this as equation 1. So let's first proceed by solving for the right hand side. So if we wanted to solve the right hand side, that means we are to solve this surface integral of curl of f vector dot n vector ds, right? So for that, what do we require? We first of all require curl of vector f. We are given vector f as x square minus y square I cap plus 2xy j cap, right? So curl of f, that would be obtained when you calculate this determinant. So it would be del by del x, del by del y, del by del z, and the quantities here. So you have x square minus y square and you have 2xy and 0 here because there is no k component here. So you have 0 k cap. So when you calculate this curl of f, it would come out to be I cap 0 minus 0, and then you have minus j cap. So it would be minus j cap 0 minus 0 and then plus k cap. It would be 2y minus 2y. So your curl of f would be equal to 4y k cap. Now you have this curl of f, so we can solve this thing. So it would be simply equal to the surface integral over curl f dot with n vector ds. So this would be surface integral over s of curl of f is this one. So we have 4y k cap dot with k cap. Why k cap? Because here the given surface is this surface in the xy plane. So this is the given surface, and what is the unit vector which is perpendicular to this? So it is given by some vector like this in the direction of z. So we have k vector here, which is the unit vector. Okay. So we have, instead of n vector, k vector, and then we have dx and dy. So when you solve this dot product, it would be surface integral over s of 4y dx dy. And we have to write what are the limits for x as well as y. Now here you can clearly see from this figure the limits for x, they vary from 0 to the point A, and the limits for y, they vary from the point 0 to the point B. So your limits of x and y, they simply are equal to 0 to B and from 0 to A for y dx dy. So when you solve this, you have 4 outside, y 0 to B. When you perform the integration with respect to x, so it would be xy and the limits of x varying from 0 to A dy. So this would be 4 ay dy integration y varying from 0 to B. So this would be 4a and y square by 2 and the limits of y varying from 0 to B. So you have, here it should be 2. So you have 2ab square. This is your right hand side. Now let's solve our left hand side. For the left hand side, we are required to calculate the closed line integral over C of the vector f dot with vector dr. Now your vector f is given to be x square minus y square I cap plus 2xy j cap and dot with vector dr. If your vector r is given by xi cap plus yj cap, because we are in only xy plane, so your vector dr would be given by dxi cap plus dyj cap. So accordingly, when you substitute the value of dr here, so it would be dxi cap plus dyj cap, right? So this would be equal to the closed integral over C. Now when you perform the dot product, this quantity would be multiplied by this. So you have x square minus y square into dx, and then this quantity would be multiplied by this. So you have 2xy dy. So now in order to calculate the line integral here, so let me draw the region again. So suppose this is your x-axis, this is y-axis, this is origin. So we have a square quantity, rectangle quantity like this. Suppose this point is A, this point is B, this point is D. So we are traversing in this anti-clockwise direction so that our direction remains positive. Now this point is a comma 0, this point is a comma b, and this point is 0 comma b, right? So these are the points that are given to us. So this integral becomes equal to the integration over the path OA of this quantity plus the integration over the path AB plus the integration over the path BD and then the integration over the path DO, right? So we have to see what are these paths first of all, and what are the limits and the values of different variables along different paths. So I can say along the path OA, I have these 2 points 0, 0 and the point a comma 0. So here the equation of line is simply given by y is equal to 0. So accordingly you have dy is equal to 0, and here x varies, and the limits for x that varies between 0 to a. So along OA we have this thing. Along AB, let's see what do we have. Here the equation of line is x is equal to a, therefore your dx become equal to 0 when you differentiate this quantity, and here y varies from the point 0 to b, right? So along the path BD, let's see what do we have here. The equation of line is equal to y is equal to b, so correspondingly you have dy is equal to 0, and here your x varies. In moving from here to here, what is the limits for x? X varies in this case from the point b to the point 0, right? Not b, the value of x is a. So from a to 0 in this case. And along DO we have the equation of line as equal to x is equal to 0, so that means dx would be equal to 0, and the limits for y in moving from here to here. Here the value of y is b, here the value of y is 0. So the limits of y, they vary from the point b to the point 0. So this is what we have. So accordingly we can write down this integration, line integration of f dot dr. So this would be integration along OA. Along OA we have this function, and along OA value of y is 0, dy is 0. So this quantity would be 0. So we are left with x square minus 0 square, and what is dx? Dx is dx only here, and the limits of x in this case vary from 0 to a. So this is first quantity. Along AB for this integral we have the value of dx as 0. So this quantity would be 0. So we are left with only 2x and y, and in place of x we will write a here. So a into y dy, and the limits of y here varies from 0 to b according to this one. Plus for the third integral we have the value of dy 0. So we won't have this second term, so we only have this first term. So for that we have y is equal to b. So x square would be as such. Then the value of y is b. So we have b square, and the value of dx would be as such. And here the limits of x, they vary from a to 0 and not from 0 to a. And for the last term along DO we have dx 0. So we won't have this first term. So we only have this second term here. So accordingly we will write it here as 2 into x into y. Now x is 0 here. So we have 0 and y and dy. So this quantity, and here the limits of y, they vary from b to 0. So we have to solve this quantity now. So when you solve this quantity, this becomes equal to the integration x varying from 0 to a of x square dx plus integration y varying from 0 to b to a y dy plus integration x varying from a to 0 x square minus b square dx plus 0, right? So this is what you have. Okay, so the integration of this first term here is equal to x cube divided by 3, and the limits of x varies from 0 to a, plus the integration here of the quantity y, it would be y square by 2, and the limits of y, they vary from 0 to b, right? and for the third quantity you will perform the integration with respect to x, so it would be this one, and here the limits of x, they vary from a to 0. So this term would be a cube by 3, and then we have 2 and this 2 and 2 cancel, so we have a into b square, and then you have b square a minus a cube by 3. So this and this got cancelled, so we have the quantity ab square plus a b square. So this quantity is 2ab square. So this is your left hand side here, right? So this is the left hand side. This is the value of the line integral. So let's have a look at what do we obtain for the right hand side. For the right hand side, we obtain the value as 2ab square. So that is what we wanted to prove here. So we have verified that the line integral of the vector quantity f dot with the r vector is equivalent to this surface integral for the vector f, and the region is defined to be this the rectangular region in the xy plane. So I hope you understood this theorem and how we can apply this theorem. So I'll see you in the next lecture. Thank you.